Hello there everyone, and welcome back to another video of our physics O-level lessons. Today's chapter is going to be forces and energy. This is our fourth chapter, and in this chapter we're going to be learning about energy and forces. We're going to learn about work, energy stores, energy pathways, conservation of energy, wasting energy, potential energy and kinetic energy, efficiency, power, thermal power stations, and energy resources. So we're going to be reading and understanding all of these topics in detail. So let's get into it right away. Starting with work. So in everyday language, work might be writing an essay or digging the garden. But to scientists and engineers, work has a precise meaning. Work is done whenever a force makes something move. And the greater the force, and the greater the distance moved, the more work is done. So, scientifically speaking, whenever we apply a force onto something and make that something move, work is done basically. So, the greater the force we apply and the greater the distance the object we are applying the force on covers, the greater is the work done. So the SI unit of work is the joule. This is represented as capital J. 1 joule of work is done when a force of 1 Newton moves an object 1 meter in the direction of the force. So this is the definition of the joule. A joule of work is done whenever a force of 1 Newton moves an object 1 meter in the direction of the force. So I hope this is very clear what the joule is and what work is. Now we're going to move on to understanding how we can calculate work. So this is the equation we use to calculate work done. Work done is equal to force multiplied by the distance moved in the direction of the force. Pretty simple, right? In symbols we write it as W is equal to F into D. F is represented as force and D means the distance. W is the symbol, small w, for work done. So, for example, if a 40 Newton force moves an object 3 meters, then the work done is 12 joules. 4 multiplied by 3, 4 ones are 4, 4 twos are 8, 4 threes are 12. So that's how we get 12 joules here. So as you can see, it's pretty simple to calculate work. So this was all about work. It's a very simple and easy thing to understand. Remember, we have to remember what work is, the definition of work and the SI unit of work, as well as the definition of the SI unit of work. Joule. 1 joule of work is done when a force of 1 Newton moves an object 1 meter in the direction of the force. And we also have to remember the equation. Surely we're going to do some questions related to it, but right now we're going to move ahead on to understanding what energy is. So, a compressed spring has energy, and so does a tank full of petrol, but both can be used to do work. So, like work, energy is measured in joules, although people talk about energy being stored or released. But let me tell you, energy isn't a thing. If, for example, a compressed spring stores 100 joules of energy, this is just a measurement of how much work could be done by the spring if the energy were released. So it's not that the spring is doing work at that moment. A compressed spring is not doing work. If it stores 100 joules of energy, that doesn't mean that it's doing work. That means that the spring is storing the energy. It is just a measurement of how much work could be done by the spring if this energy was released. Energy can be stored in different ways. So here we have 2 different ways we can store energy. Moving objects store energy. For example, a moving ball can do work by knocking something over because it has energy stored in it. And materials are made up of particles that are constantly in motion. For example, in a solid, the particles are vibrating. If the solid is heated, its temperature rises and the particles move faster. So this is how a moving object stores energy. when a ball is moving, it can knock something over. So that means that it does have energy to make any other object move. And the second point is that materials are made up of particles and are constantly in motion. This also applies to the ball. Of course, if the ball is moving, its particles are also in motion. So, for example, in a solid, the particles are vibrating. If the solid is heated, its temperature rises and the particles move faster. This means that the energy is being released in the form of heat energy. Because the temperature rises, the particles move faster. So it sometimes helps to add a label to the word energy to describe how it is being stored. Here are the names used to describe the different energy stores. So firstly, we have kinetic energy. So this is the energy stored by an object because of its motion. Just like we were talking about the ball. The ball, when moving, can do work by knocking something over. So kinetic energy releases when an object moves. So it is the energy stored by an object because of its motion. So when a person moves, kinetic energy is being released. The second example, here we have more names. Gravitational potential energy. This is the energy stored by objects lifted upwards against the force of gravity. And this is released when they fall downwards. So we always have gravitational potential energy inside us because it is the energy that keeps us on the ground. So if we lift an object upwards against the force of gravity, and when we leave it, it falls downwards. So what happens is that gravitational potential energy gets released when they fall downwards. That is why they fall downwards. So gravitational potential energy is related to gravity. Next we have elastic energy. Elastic energy is like when we stretch a rubber band or compress a spring, they both store energy. So that kind of energy is called elastic energy. And then we have chemical energy. This describes energy stored in the chemical bonds between atoms. Obviously, atoms have chemical bonds, that is why they are together. Like in solids, they have stronger chemical bonds, in liquids they are weaker, and in gases they are much weaker. There must be some sort of energy that keeps the atoms bonded together, and that is called chemical energy. There are many more energies we have to go through, like we have nuclear energy. So an atom has a nucleus at its center, and this is made up of particles bound together by strong forces. In some atoms, if the particles become rearranged or the nucleus splits, stored energy is released. So the nucleus of the atom stores this nuclear energy. What happens is that when atoms are split, the nucleus splits, of course, and the stored energy, the nuclear energy, is released. Nuclear energy is very big. It's like very high in atoms, in a single atom even. And we use this energy in nuclear power stations. We're going to read more about that in another chapter. But now let's move ahead onto thermal energy. Of course, in all materials, the particles are moving, so they store energy. So when a hot object cools, its particles slow down. So some of the stored energy is released. People normally call it heat. So when you heat a solid object, its particles vibrate vigorously. And what happens is that they release thermal energy. We can call it heat, but that heat that is being spread out from that object is thermal energy being released. After this, we have electrostatic energy. If electric charges attract each other but are held apart, they store energy. Say for example, a positive charge and a negative charge. They attract each other but they are held apart. For example, negative charge is on a different object and the positive charge is on a different object. They are held apart, so they store energy. This is the energy of attraction. Also, electrostatic energy is also when two light charges are together, they repel each other. So that is also electrostatic energy. Then we have magnetic energy. Like if two magnets attract each other but are held apart, they store energy. So we do know what magnets are. We have played with them in our childhood as well. So when we bring two magnets close together, like the opposite poles close together of the magnet, they attract each other, but if we keep them at a distance, they are held apart, so they store energy. And in the same way, if we bring two like poles of the magnet together, they would repel. So that is also magnetic energy. So in many of these energy stores, objects or particles store energy because of their position. The general name for this is potential energy. Okay, this was potential energy. Now that we've understood energy stores, different types of energy stores, we've read all of them, we can move ahead on to understanding energy pathways. Everywhere around us, things are rising, falling, speeding up, slowing down, heating, cooling, charging, discharging, burning. In other words, energy is being transferred from one store to another. By transfer, we mean shift. So, all of these things like rising, falling, speeding, slowing down, heating, cooling, charging, discharging, burning, all of these are basically energy being transferred from one store to another. So now we're going to understand the 4 pathways energy can take to get transferred from one store to another. The first pathway is mechanically by a force moving something. Like when we push an object, we have a force which moves the object. So this is when energy gets transferred mechanically. Like I transferred my energy through my hands. So this is energy being transferred mechanically. Then we have electrically by a current. Like wires and different electric systems, we have energy being transferred by electric current. Lights and fans and other electric things are connected by electricity. If we don't have any electricity, those things won't work. So what happens is that energy is being transferred by a current into the objects we use, into the electronic objects we use. Then we have by heating because of a temperature difference. Okay, this is kind of like thermal energy. So what happens when a hot object is placed near to a cold object, like a normal temperature object, the energy of that hot object is transferred to that other object because of a temperature difference. What happens is that the other object, which was normal in temperature, also begins to heat up. So this is another energy pathway by heating. And the last energy pathway is by radiation, such as light waves and sound waves. So yes, of course, when I speak, energy is being released. This is energy being transferred by radiation. By radiation, we mean any kind of wave, sound waves or light waves. So these are basically radiations, light waves as well. When we turn on light, energy is being transferred by radiation or any kind of light. It doesn't matter if it's from a bulb or from the sun. It is just energy being transferred from radiation, which makes us see objects. Sound waves as well. So these were the 4 energy pathways that energy takes to get transferred from one store to another. Now we're going to move ahead on to understanding conservation of energy. So money doesn't disappear when you spend it. It goes somewhere else. In the same way, energy never disappears. People talk about using energy, but what really happens is that the energy is moved from one store to another. Transferred, what we were just learning a minute ago. Energy pathways. So energy is transferred from one store to another. It never disappears. So energy is never used or disappeared. It is only moved from one store to another store. For example, a girl throws a stone in the air. So what happens is that the chemical energy stored in her muscles turn to kinetic energy when she does the action. When I move an object, energy from me is mechanically being transferred to that object. This is what happens here, that when the girl throws the stone in the air, the chemical energy stored in her muscles turn to kinetic energy when she does the action. because movement occurs. So the stone also gains kinetic energy when it moves upwards. Because it is moving, kinetic energy is released when an object is moving. And then the kinetic energy turns into gravitational potential energy when it reaches its highest point and starts falling downwards. Right, when the object is at its highest point, gravitational potential energy releases because the force of gravity acts downwards and the object, the stone, starts to fall downwards. That is gravitational potential energy being released. During its fall, the GPE, gravitational potential energy, is again converted into kinetic energy because again the object is moving and the stone hits the ground. The kinetic energy turns into thermal energy when it hits the ground because it makes the particles in the ground move faster, mostly because of friction. So the materials warm up a little. That is how thermal energy is released. So when the stone hits the ground, friction makes the particles in the ground move faster. So the materials, both the stone and the ground, warm up a little. So during each transfer, the total quantity of energy stays the same. And this is an example of the law of conservation of energy. That energy is conserved. Energy can be stored or transferred, but it cannot be created or destroyed. So this was conservation of energy. Okay, so in reality, at the different stages of energy transfer of the stone we were just talking about, some energy is transferred elsewhere. Remember, it is not used up, it is transferred elsewhere. For example, muscles action transfers less than 20% of the energy stored in your food to a kinetic store, and the rest is wasted as thermal energy, which is why you heat up when you exercise. And when an object moves through air, some energy is transferred to a thermal store because of friction. Air resistance. We have read about this before. This comes as a force. Air resistance. It is a frictional force. Even energy transferred by sound waves ends up being stored thermally. So the stone, ground, and surroundings become a little warmer than before. Because when the stone hits the ground, it also creates a sound. That sound is also stored thermally. Okay, so despite the energy dissipated, wasted, the law of conservation of energy still applies. The total quantity of energy is unchanged. It might be less than before, but you should know that the percentage of energy that is less than before is not disappeared, has not disappeared or finished. It has moved somewhere else. In other words, it is wasted. By wasted, we do not mean finished or disappeared. We mean that it has moved to somewhere, that it is transferred to any other stage. For example, it is transferred into thermal energy. So here we have a Sankey diagram. So this is basically an arrow like this one. This is the arrow which shows the energy transfers. And these arrows, these ones over here, show the wasted energy. So when the stone is thrown upwards, kinetic energy is released. When the kinetic energy is released, some of the energy is wasted as well. This is wasted in the body. When the stone is moving upwards, the energy is being released as thermal energy as well. It is wasted in the body of the stone. When the stone reaches its highest point, gravitational potential energy is released. And some of the energy is wasted as well because of air resistance. This is not much, as you can see, than thermal energy in the body. It's very less. But then when the stone starts to fall downwards, kinetic energy is again released and the thermal energy is also released because of air resistance. And then the stone hits the ground. And when it hits the ground, thermal energy is released in the ground and the stone. But some energy is again wasted. This is thermal energy as well, transferred by sound waves. This is the wasted energy when the stone hits the ground. So these were the wasted energies. By this we can see that the law of conservation still applies because the energy is not destroyed. it is moved somewhere else. It is moved into the thermal energy, as you can see. Most of them are the thermal energy, which are either transferred by sound waves, wasted because of air resistance, wasted in body, in muscles. It is still heat which is wasted. Heat energy which is wasted. Okay, so now that we've understood the conservation of energy and how energy is wasted, we can move ahead on to understanding work done and energy transferred. So a brick is dropped. As it falls to the ground, it loses height and speeds up. Before it falls, it has 20 joules of energy in its gravitational potential energy stored. So when it is about to strike the ground, all 20 joules has been transferred to its kinetic store. So when we look at it in another way, 20 joules of work has been done by the force of gravity. So whenever work is done, work done is equal to energy transferred, which means, as you saw, the brick had 20 joules of energy stored as the gravitational potential energy. When it fell to the ground, it speeded up, and when it was about to strike the ground, all of the 20 joules of energy were transferred to its kinetic store. So what happened was that when the work was done by gravity, of course it was gravity which was moving the object downwards, the work done was equal to energy transferred, because energy that was transferred was 20 joules. From the gravitational potential energy, it got transferred to the kinetic energy. So what it basically means that if 20 joules of energy are transferred, then 20 joules of work has been done. And this is what it basically means. We can put it as an equation that work done is always equal to energy transferred. If the energy transferred was 100 joules, then 100 joules of work would have been done. So work done is equal to energy transferred. Okay, now that we've understood this, we can move ahead on to doing a question. In other words, we can learn how to calculate PE and KE. PE is potential energy and KE is kinetic energy. So we have the example here. A ball is suspended in the air. So it has potential energy because of the Earth's gravitational pull. This is called gravitational potential energy. We also call it PE. So if the ball is released, it falls and gains kinetic energy, KE. So both PE and KE can be calculated. And how do we do that? Let's get on to it. The gravitational potential energy of the ball is equal to the work which would be done if the ball were to fall on the ground. We know that work done is equal to energy transferred. We just read it. Energy transferred is equal to work done. Both are equal. So the gravitational potential energy of the ball is equal to the work which would be done if the ball was to fall on the ground. Right now it is suspended in air. Assuming no air resistance, it is also equal to the work done in lifting the ball a distance h up the ground in the first place. What this basically means is trying to say that when we lifted the ball from here to here, work was done, and that work done was also equal to the gravitational potential energy of the ball. Lifting the ball and releasing the ball both has kinetic energy being played, so the work done is equal to the energy transferred. This is a distance from the ball to the ground. We call it h. So what we are going to do, we are going to calculate the PE of this ball, gravitational potential energy. And to do that, this is the method. Downward force on the ball is equal to the weight of the ball, which is equal to mg. We know that the downward force on the ball is equal to the weight of the ball. And the equation we use to find the weight of the ball is the mg equation. Weight is equal to mg, mass into gravity. So the downward force on the ball is equal to mg. So the upward force needed to lift the ball is also mg. Of course, it is the same. It is the same height. It is the same work done. So work done in lifting the ball is equal to force into distance moved, which is equal to mgh. So now instead of mg, we have mgh. So because this work done is equal to force into distance moved is equal to mgh. So for an object of mass m at a vertical height h above the ground, gravitational potential energy is equal to mgh. Gravity comes in as well. Of course, gravity is pretty simple. It's 10 Newton meters, always, on the earth of course. So we multiply the mass of the ball by the gravitational field strength, which is 10, and by the height, and that gives us the gravitational potential energy this ball has. So whatever the gravitational potential energy the ball would have would be equal to the work which would be done when the ball would fall on the ground, and also equal to the work done when the ball was picked up in the first place. So this is the equation of gravitational potential energy, mgh. Pretty simple, right? Now we're going to understand how we can calculate kinetic energy. So the kinetic energy of the ball is equal to the work which the ball could do by losing all of its speed. Assuming no air resistance, it is also equal to the work done on the ball in increasing its speed from 0 to a different speed. We can call it v. So what we're saying here is that work done is equal to force into distance moved. Work done is equal to mass into acceleration into distance moved. Work done is equal to mass into gain in speed divided by time taken into average speed into time taken as well. Work done is equal to mass into gain in speed into average speed. Work done is equal to m into v into half v. Work done is equal to half mv square. So, for an object of mass m and speed v, kinetic energy is equal to half mv square. Okay, so here we have an example. If a 2 kg mass has a speed of 3 meters per second, the kinetic energy is equal to half into 2 kg into 3 meters per second square. Remember, 3 is a square. So this is equal to half into 2 into 3 square joules, which is equal to 9 joules. So this is the equation we use to measure kinetic energy, half mv square. This means that mass multiplied by velocity in the power of 2 divided by 2. By half we mean dividing by 2, of course, making the measurement in half. And so we use it to find the kinetic energy by using the mass and the speed of the object. Mass multiplied by speed in the power of 2. Remember, the speed is in the power of 2. We multiply both the values and divide it by 2, and we get 9 joules. So this was kinetic energy and potential energy, how we can measure both these things. I hope it was simple and it was clear. So we can move ahead now on to understanding scalar energy. By scalar energy, we mean energy is a scalar quantity, which means that it has magnitude but no direction. So you do not have to allow for direction when doing energy calculations. So here we have object A and object B. They both have the same mass and are at the same height above the ground. So B was lifted vertically, but A was moved up a smooth slope. Although A had to be moved further, less force was needed to move it, and the work done was the same as for B. So as a result, both the objects have the same potential energy. The potential energy is equal to mgh. So the potential energy depends on the vertical gain in height and not on the particular path taken to gain that height. The potential difference remains the same for both the objects because the vertical gain in height is the same of both the objects, except for that the object A has a path like this and object B has a vertical path. Okay, now let's do some questions about potential energy and kinetic energy. So, if a 4 kg stone is dropped from a height of 4 meters, what is its kinetic energy when it has fallen halfway to the ground? So, the mass of the stone is 4 kg and the height it is dropped from is 4 meters. And it is asking that what is its kinetic energy when it has fallen halfway to the ground. So, when the stone falls, its gain in kinetic energy is equal to its loss in potential energy. So you can calculate that instead. So height lost by the stone is 2 meters. Halfway to the ground is obviously 2 meters. So the gravitational potential energy is equal to mgh, which is 4 kg multiplied by 10 Newton per kg multiplied by 2 meters. and we get 80 joules. So the gravitational potential energy is 80 joules, halfway to the ground. So the kinetic energy gained by the stone is 80 joules as well. As the stone started with no kinetic energy, this is the stone's kinetic energy halfway down, because its gain in kinetic energy is equal to its loss in potential energy. So the gravitational potential energy is lost. 80 joules of gravitational potential energy is lost, so it is equal to the gain in kinetic energy, 80 joules. So this was very simple. I mean, only if the stone had started with no kinetic energy. So this basically tells us that the loss in potential energy is equal to the gain in kinetic energy. So now we're going to move ahead on to another question. If a 4 kg stone slides down a 5 meter tall smooth slope, what is its speed when it reaches the bottom? Okay, so at the top of the slope, the stone has an extra gravitational potential energy. And when it reaches the bottom, all of its potential energy has been transformed into kinetic energy. So what happens? Gravitational potential energy at the top of slope is equal to mgh, which is equal to 4 kg into 10 into 5 meter, the distance. This is the height, this is the mass, and this is the gravity. We multiply all three of the values and we get 200 joules. So half mv square is equal to 200 joules. So half into 4 kg into v2 is equal to 200 joules. And this gives v is equal to 10 meter per second. So we basically broke down values. So by rearranging the equation half mv square, we can find the velocity of the stone. This gives the velocity of the stone equal to 10 meter per second. So the stone's speed at the bottom of the slope is 10 meter per second. So this was also easy. What we did in this was again found the gravitational potential energy at the top of the slope. This is what we did, and the loss in gravitational potential energy is equal to the gain in kinetic energy. So 200 joules is the kinetic energy of the stone when it reaches the bottom. But it told us to find the speed when it reaches the bottom. So to find the speed, we rearranged the kinetic energy equation and we found that v is equal to 10 meter per second. So this is how we found the stone speed at the bottom of the slope. So these were the two questions we did now. And now that we've understood how we can calculate potential energy and kinetic energy in different kind of ways, like using potential energy to find kinetic energy and using kinetic energy to find potential energy, and the equations of kinetic energy and potential energy. Now that we've understood all of this and practiced it a little, we can move ahead on to understanding efficiency. So engines and motors do work by making things move. Petrol and diesel engines need the energy stored in their fuel. Electric motors rely on the energy transfer from a battery or generator. The human body is also a form of engine. It needs the energy stored in food. So, an engine does useful work with some of the energy supplied to it, but the rest is wasted as thermal energy. So, in physics, efficiency refers to the ratio of useful output to the total input in a particular process or system. It is measured of how well a system or device converts input energy or resources into useful work or output. By this we mean that how much energy the device wastes. If it wastes less energy and converts the input energy into more useful work or output, then its efficiency is good. It means its efficiency is high. So mathematically, efficiency is often represented as a percentage and can be calculated using this formula. Formula is efficiency is equal to useful work done divided by total energy input multiplied by 100. Of course, to find a percentage, we have to multiply by 100. And the second is that useful energy output divided by total energy input multiplied by 100. So for example, if a petrol engine does 25 joules of useful work for every 100 joules of energy supplied to it, then its efficiency is 1/4 or in other words 25%. Its useful energy output is 1/4 of its total energy input. This is the equation we use to find the efficiency. Useful energy output divided by total energy input, or useful work done divided by total energy input. They both mean the same things. So this was efficiency. Now, to understand the other formula we use to measure efficiency, we have to understand power first. So what is power? A small engine can do just as much work as a big engine, but it takes longer to do it. The big engine can do work at a faster rate. So, power refers to the rate at which work is done, or the rate at which energy is transferred or converted in a system. So, it measures how quickly energy is expended or produced in a given amount of time. So, power is basically the rate at which work is done, simply. The SI unit of power is the watt. This is represented as capital W, which is defined as 1 joule of work per second. So this is the definition of the watt here. 1 joule of work per second is equal to 1 watt. So for example, if an engine does 1000 joules of useful work in 2 seconds, its power output is 500 watts, 500 joules per second. So mathematically, power can be calculated using this formula. Power is equal to work done divided by time taken. So the symbol for power is P, but the symbol for watt, which is the SI unit of power, is capital W. Remember, don't confuse this watt with the work done over here. So work done divided by time taken is equal to power. Alternatively, for systems where energy is transferred or converted, the formula for power can be expressed as energy transferred divided by time taken, rather than work done. So power is a scalar quantity, meaning it has only magnitude and no specific direction. So, as energy and power are related, there is another way of calculating the efficiency of an engine. Efficiency can be calculated using this formula, which is useful power output divided by total power input. So in this formula, we are writing useful power output, not energy output or work done. It is useful power output divided by total power input. So when we divide these two and then multiply by 100, we get the efficiency of the engine. So this was another formula we used to find the efficiency of a device. Okay, so now that we've understood power and efficiency, we can move ahead onto doing some questions related to power. Some power problems. Example 1. A crane lifts a 100 kg block of concrete through a vertical height of 16 meters in 20 seconds. If the power input to the motor is 1000 watts, what is the efficiency of the motor? Okay, I want you guys to work this question out. I have the answer written over here, but it is your job to use the equations. As we have read all the equations, understood all of them, we can use those equations to find the answer to this question. I also have it all written down here. So if you have found the answer right now, let me read it out how we can get the answer. On Earth, G is 10 Newton per kg. So a 100 kg block has a weight of 1000 newtons. So simple, we just found the weight of the block because the weight is equal to m into g, mass multiplied by gravity. So 100 kg multiplied by 10 and we get 1000 newtons. Therefore, a force of 1000 newtons is needed to lift the block. So when the block is lifted, work done is equal to force into distance. So 1000 newtons, which is the force, and the vertical height, which is the distance, 16 meter, they get multiplied together and we get the work done, which is 16,000 joules. So to find the useful power output, we divide the useful work done by the time taken to do that work. So we divide 16,000 joules by 20 seconds and we get 800 watts. So here comes the power output equation. And we had the work done equation. We also had the weight equation involved in this question. And lastly, we have the efficiency. So to find the efficiency, we divide useful power output by total power input, which means divide 800 watts by 1000 watts because the power input to the motor is 1000 watts. So when we divide both the values together, we get 0.8. Of course, we have to multiply this by 100 afterwards. 0.8 multiplied by 100 and we get 80%. So the motor has an efficiency of 80%. So this is how we use different equation in a specific question to find out the answer. Okay, so this was one question. Now we're going to do another example. A car has a steady speed of 30 meters per second. If the total frictional force on this car is 700 Newton, what useful power output does the engine deliver to the driving wheels? Okay, so the speed of the car is 30 meters per second. Here's what we have. The total frictional force on the car is 700 Newton, and it's asking us to find the useful power output that the engine delivers. So, as the speed is steady, the engine must provide a forward force of 700 Newton to balance the total frictional force. Of course, if the speed is steady, this means that the speed is constant, it is not changing. The speed is the same every second, which means that the engine must provide a forward force of 700 Newton to balance the total frictional force. Because this total frictional force is 700 Newton, so the forward force should be 700 Newton as well to balance it out. So, we just found the forward force of the car. In 1 second, the 700 Newton force moves 30 meters because the speed is 30 meters per second. So, work done is equal to force into distance, which means we multiply 700 Newton by 30 meters and the work done is 21,000 joules. Now, as the engine does 21,000 joules of useful work in 1 second, its useful power output must be 21,000 watts. We don't even have to put the equation here because the time taken is only 1 second. So 21,000 joules of useful work done divided by 1 and we get 21,000 watts or 21 kilowatts. We can also write it like that. So here's how we just solved this problem. Now let me tell you this. Problems of this type can also be solved using this equation. Like we did all of this stuff, this is also correct, but we can also use this equation, which is useful power output is equal to force into speed. So the total forward force multiplied by speed and we get the useful power output. So we just have to multiply 700 Newton by 30 meters per second and we would have got the useful power output. So these two questions we have done successfully and I hope you have understood them nicely. How we use different equations and how we go through different steps and how we have to find different things in order to find that particular thing question is asking us to find. So now we can move ahead on to understanding thermal power stations. Industrial societies spend huge amounts of energy. Much of it is supplied by electricity, which comes from generators in power stations. So, in most power stations, the generators are turned by turbines blown round by high-pressure steam. To produce this steam, water is heated in a boiler. So, the thermal energy comes from burning fuel or from a nucleus reactor. Nuclear fuel does not burn. It's energy released by nuclear reactions which split uranium atoms. Like we just read before, nuclear energy is also a form of energy store. And when an atom is split in half, lots of energy is released. So this is what happens. Energy is released by nuclear reactions which split uranium atoms. This process is called nuclear fission. We're going to read more about this nuclear reactions in our radioactivity chapter. It's very fun to understand it as well. Once the steam has passed through turbines, it is cooled and condensed so that it can be fed back to the boiler. So what happens is that in thermal power stations, The generators in the stations are turned by turbines, and the turbines are blown round by high pressure steam. To produce this high pressure steam, water is heated in a boiler, and the thermal energy which is needed to heat the boiler comes from a nucleus reactor. What happens is that nuclear reactions which split uranium atoms release large amounts of energy. So this energy is then used to heat the water in the boiler, and then the steam from this boiler is used to turn the turbines. It is a high pressure steam. So here we have what I'm talking about. So once the steam has passed through the turbines, it is cooled and condensed, which means it is turned back into liquid so that it can be fed back to the boiler. Some of the power stations have huge cooling towers with drafts of air up through them. Others use the cooling effect of nearby sea or river water. So, of course, thermal power stations waste a lot of energy. Thermal power stations waste more energy than they deliver. Most is lost as thermal energy in the cooling water and waste gases. For example, the efficiency of a typical coal-burning power station is only about 35%. In other words, only about 35% of the energy in its fuel is transformed into electrical energy. The rest is wasted. Like energy is lost in boilers, energy is lost in turbines. As heat energy, of course, energy is lost in generators. Energy is also lost to one power station. It's all heat energy, which is being wasted. So, engineers try to make power stations as efficient as possible. But once energy is in thermal form, it cannot all be used to drive the generators. This is a disadvantage. Thermal energy is the energy of randomly moving particles, such as atoms and molecules. So it has a natural tendency to spread out. As it spreads, it becomes less and less useful. So, for example, the concentrated energy in a hot flame could be used to make steam for a turbine. But if the same amount of thermal energy were spread through a huge tank full of water, it would only warm the water by a few degrees. So, this warm water could not be used as an energy source for the turbine. But this unused thermal energy from a power station does not have to be wasted. Using long water pipes, it can heat homes, offices, and factories in the local area. This works best if the power station is run at a slightly lower efficiency, so that hot water is produced. Okay, so this was about thermal power stations. We can look at some reactions for energy. So when fuels burn, they combine with oxygen in the air. With most fuels, including fossil fuels, the energy is released by this chemical reaction. Firstly, when the fuel is combined with oxygen, it burns and forms carbon dioxide and water. Water and carbon dioxide are waste gases basically. And fuel and oxygen are used up to form these. They both are waste gases and we get thermal energy. This thermal energy is then used to heat the water. And most of the thermal energy is wasted. Well, we can't say it's wasted, it is still used to heat homes and offices in the local area. But still, the efficiency of the thermal power stations are less. Okay, here we have some pollution problems of the thermal power stations. Thermal power stations, of course, can cause extra pollution in a variety of different ways. Firstly, fuel-burning power stations put extra carbon dioxide gas into the atmosphere. And this traps the sun's energy and is adding to global warming. The sun's energy is basically trapped over there. It is not getting released. So what happens is that the earth is slowly cooling down, which means that we are having global warming. Coal-burning power stations emit almost twice the amount of carbon dioxide per kilojoules output compared with those burning natural gas. Okay, so this was one point, that they put extra carbon dioxide gas. The second point is that unless low sulfur coal is used or desulfurization units are fitted, coal-burning power stations emit sulfur dioxide, which is harmful to health and causes acid rain. So unless these things are used, power station emits sulfur dioxide, which is harmful to health. Thirdly, transporting fuels can cause pollutions. For example, there may be a leak from an oil tanker. The fourth problem is that the radioactive waste from nuclear power stations is highly dangerous. It must be carried away and stored safely in sealed containers for many years, and in some cases, thousands of years. Nuclear accidents are rare, but when they do occur, radioactive gas and dust can be carried thousands of kilometers by winds. Okay, these were the pollution problems that thermal power stations cause. We're going to understand power from water and wind. So some generators are turned by the force of moving water or wind. There are 3 examples. Power schemes like this have no fuel costs and give off no polluting gases. So these are the advantages. However, the disadvantage is that they can be expensive to build and need large areas of land. Compared with fossil fuels, moving water and wind are much less concentrated sources of energy. So we have the hydroelectric schemes. These use the GPE of waters on hills to generate electricity as it flows downhill. So river and rainwater fill up the lake behind this dam, as you can see. And as water rushes down from the dam, it turns turbines, which turn generators. And then we have the tidal power scheme. The lake behind this dam, as you can see, fills when the tide comes in and empties when the tide goes out. The flow of water turns these generators. So this was how we use water to form power. We use power from water, and here we have the wind farm. So this is a collection of aerogenerators. Generators driven by giant wind turbines. Basically, wind is used over here. So these were the simple schemes and wind farms which use water and wind to form energy. Okay, this was all about that. Now we can move ahead on to understanding energy resources. Most of the energy that we use comes from fuels that are burned in power stations, factories, homes, and vehicles. So nearly all of this energy originally comes from the sun. The sun is 75% hydrogen. It releases energy by a process called nuclear fusion. So the energy resources we use on Earth can be renewable or non-renewable. For example, wood is a renewable fuel. Once it is used, more can be grown to replace it. Oil, on the other hand, is non-renewable. It took millions of years to form in the ground and cannot be replaced. So, let's look at some non-renewable energy resources. Fossil fuels and nuclear fuels. They both are non-renewable energy resources. In fossil fuels, we have coal, oil, and natural gas. They formed from the remains of plants and tiny sea creatures that lived millions of years ago. So they are very concentrated sources of energy. Petrol, diesel, and jet fuel are all extracted from crude oil, and it is the raw material for making most plastics. Nuclear fuels. Most nuclear fuels contain uranium. So in nuclear power stations, the energy is released by fission, a process in which the nuclei of the uranium atoms are split. Nuclei of uranium atoms are split. We just read about this. When they are split, they release large amounts of energy. They are used in nuclear power stations. So these are the non-renewable energy sources, fossil fuels and nuclear fuels. Then we have the renewable energy resources. So we have a long collection of these here. And we're going to go through them one by one, as well as reading out the problems they have. So firstly, we have hydroelectric energy. A river fills a lake behind a dam. Water flowing down from the lake turns the generators. This hydroelectric energy, we just saw the scheme behind as well. But the problem is that these schemes are expensive to build, and few areas of the world are suitable. So flooding land and building a dam causes environmental damage as well. So these are the problems here. So hydroelectric energy is a very useful way of producing energy, but it is expensive to build and it needs a lot of area. So then we have tidal energy, which is similar to hydroelectric energy. The difference is that a lake fills when a tide comes in and empties when it goes out. The problems it has are the same as for hydroelectric energy. Then we have wind energy. So generators are driven by wind turbines, windmills. The problems of this is that large, remote, windy sites are needed, and winds are variable, of course. There sometimes might be huge amounts of winds, and sometimes there might be no wind at all. So the wind turbines are noisy and can spoil the landscape as well. Next we have wave energy. This is when generators are driven by up and down motions of the waves at sea. Okay, so this is a different kind of wave. The problem with this is that it is difficult to build and few devices have been successful. After this we have geothermal energy. Geothermal means heat from the earth. So water is pumped down to hot rocks deep underground and rises as steam. So in areas of volcanic activity, the steam comes naturally from hot springs. But the problems of this is that deep drilling is difficult and expensive. Then we have solar energy, which is energy radiated from the sun. So solar panels absorb this energy and use it to heat water. Solar cells are made from materials that can deliver an electric current when they absorb the energy as light. Such fascinating things, aren't they? Well, surely the problems are big. Variable amounts of sunshine in some countries. That's one problem. Solar cells are expensive and must be large to deliver useful amounts of power. A cell area of around 10 meters square is needed to power an electric kettle. So this was the solar energy. Last but not the least, we have the biofuels. These are fuels made from plant or animal matter. They include wood, alcohol from sugar cane, and methane gas from rotting waste. So the problems of this is that huge areas of land are needed to grow plants. So this was another example of renewable energy resources. So these were all the renewable energy resources that we've just understood now. So this was forces and energy. We have successfully completed this chapter today, and we have understood these topics from this chapter in detail. Let's go through a summary of chapter 4. First we learned work, the SI unit of work, how the joule is described. 1 joule of work is done when a force of 1 Newton moves an object 1 meter in the direction of the force. We learned the equation we use to measure work done. Then we understood energy, how we can measure energy, what is the SI unit of energy, how this energy can be stored in different ways. Then we read the energy stores, the different energy stores. Gravitational potential energy, nuclear energy, thermal energy, many other more. Magnetic energy, electrostatic energy. And after this, we understood energy pathways. How the energy is transferred or shifted from one store to another. We understood the 4 pathways energy takes: mechanical, electrical, by heating, and by radiation. Then after this, we understood the conservation of energy, that the energy is never used or disappeared. It is only moved from one store to another. We read an example of this that proves this law of conservation of energy. Then we understood how energy is wasted. And then we understood work done and energy transferred, the relation between both of them, that they are equal. Work done is equal to energy transferred. After this, we understood how we can calculate potential energy and kinetic energy. we learned the equations we used for potential energy, like mgh, and the kinetic energy equations, half mv square. Then we understood that energy is a scalar quantity. And then we did questions related to potential energy and kinetic energy. We used all the equations we learned in this chapter in these questions, like the efficiency, the work done equations. We used the equation gravitational potential and kinetic energy. How we can use these equations to find the answers to these questions. And after this, we understood efficiency, how efficiency is calculated, and after this, we understood power, the SI unit of power, how power can be calculated using these formulas. And after reading power, we also found another way of calculating efficiency of an engine by useful power output divided by total power input. So after this, we did some power problems in which we used the work done equation as well as the power equations and the efficiency equations. We did two big questions, and after this, we understood thermal power stations. What thermal power stations are, the different steps of the thermal power stations, how it is done, how the generators provide electricity, what the unused thermal energy from the power station does, and the reactions for energy, and the reaction for energy. After this, we read about the pollution problems thermal power stations cause. A lot of pollution problems. And then we understood how we can make power from water and wind, the different ways we could do this. And then we understood energy resources, that the non-renewable and renewable energy resources. Non-renewable energy resources are fossil fuels and nuclear fuels, and the renewable energy sources are many. We read them one by one along with their problems, but it is a fact that these resources, these energy resources, are much better than thermal power stations or nuclear power stations, as they are harmless to the environment. So, this was the chapter 4 of our physics O-level lessons, and we have completed it as well as done its summary. I hope you have understood all the equations I wrote in this and how we can use these equations to do questions. It was very clear, the equation of efficiency, the equation of power, and the equation of work. And I hope you're going to be using these equations in many different questions. This was all about chapter 4. And the next chapter is going to be thermal effects. So I'll see you in the 5th chapter in the next video.